Hey everybody, and welcome back to another edition of the Data Idols and Data Science Festival Summer School. I'm Jess, the Community Director at the Data Science Festival and head up the team that put this summer school together. So today you are able to watch this session two ways. You can either watch it live, and if you are doing that, in a second you'll see in the chat our link to the Slack channel. Please join that and please use it if you've got questions or comments. It's also a chance to kind of network and see who else is watching the sessions. And these courses will be run for the next sort of 3 months. Or if you're watching this on playback, thank you so much for joining us again. And hopefully you found some other sessions that you can also watch and study. So the Data Idol Summer School is a brand new initiative, and it's only been possible to create with the support of these fantastic partners. So just wanted to say a massive thank you to every single one of them. The speakers in the team here have put in about 400 hours of volunteer work to get this off the ground. So we are extremely grateful to every single speaker and every single company who's taken part in this year's event. So this session is actually in partnership with Royal Mail. They've been fantastic partners for the last few years. You may have watched previous sessions with them. They're always great and they're a lovely company to work with. So this session is Introduction to Neural Networks, and it's going to be covered by Timothy and Annelies from Royal Mail. So I hope you enjoy, and we'll see you at another event soon. Thank you.
Hi, I'm Timothy Flack, and I'm a data scientist at the Royal Mail. And me and my colleague, Annelies, will be giving you an introduction to neural networks today. Okay, so let's begin. Okay, so what we're going to go through today. So the contents of today is I am going to go over a brief history of neural networks, a comparison of traditional machine learning models versus neural networks. We will further introduce what a neural network is and consists of, discuss some activation functions, some learning and loss functions, and then we will look at the functionality of a simple neural network and discuss that with a simple Python example. I will then pass this presentation over to my colleague, Annelies, who will go over networks of memory, recursive and long short-term memory networks, and then some convolutional neural networks. We will jump back to me. I will go through a simple example of using a convolutional neural network, and then we will wrap it up, and that will be that. So the history of neural networks can be traced back to 1943, when Warren McCulloch and Walter Pitts created a computational model for neural networks based on threshold logic. This steadily increased the research until the 80s, where there was a brief hiatus where progress on neural network research was halted for a bit. But then we sort of draw into the mid to late 80s, 90s, and there was some great research and great breakthroughs, particularly Jan LeCun and his work on gradient-based learning. So now we know that neural networks are all over the place when it comes to data science. They're very interesting, and yeah, that's why we're here today, to go over some neural networks. Okay, so let's have a look at the difference between traditional ML models and neural networks. So what does, when I say ML, machine learning, what does an ML model do? It transforms its input data into some meaningful output. So here we can see sort of a diagram on the right where we've got traditional programming, where we give it some input and a program, and we get some output. But what we're trying to do with machine learning is give it the input and some output and generate a program. So central to machine learning and deep learning is to meaningfully transform data from one representation to another. So this learning of how to transform from one representation to another comes from exposure to known examples of inputs and outputs. So representations of data are just different ways to look at data. For example, you could have the RGB format, red, green, blue for an image, or the HSV format. They're two different formats of the same data. And some representations are obviously more appropriate for different tasks. So ML models are about finding appropriate representations for their input data. And traditional ML models aren't usually creative in finding these transformations. They're usually searching some set of predefined set of operations called a hypothesis space. So in summary, machine learning is searching for useful representations of input data within a predefined set of possibilities using guidance from some feedback signal, which we get from comparing our output to the real outputs. So when we talk about deep learning compared to traditional ML models, what do I mean when I refer to deep or depth? So the depth of an ML model is how many representations of the data the model utilizes, and this is often referred to as layers. So traditional machine learning involves one or two layers of representations, or layers or representations of the data, and this is sometimes called shallow learning. So in the picture on the right, you can see a very simple neural network where you have an input layer, a hidden layer, and then an output layer. So there are 3 layers here for a simple neural network. And deep learning models is the process of learning successive layers of increasingly meaningful representations. So in deep learning, these layered representations are learned via models called neural networks. So in summary, deep neural networks map inputs to targets or outputs via a deep sequence of simple data transformations, which are our layers that do the transformations, and that these transformations are learned by exposure to examples. So why deep learning over traditional machine learning? So deep learning offers better performance on many problems when compared to traditional ML models. And this could be anything from image and speech recognition to medical diagnosis, self-driving cars, and many more applications. But why do they perform better? So shallow learning ML models usually involve transforming the input data into one or two successive representations, usually via simple transformations. So for example, support vector machines. But the refined representations required by sort of complex problems, so ones that the examples I just mentioned, generally can't be attained by such techniques. And anyone who's done any machine learning will know that we all go to great lengths to make the initial input data more amenable to processing by these methods. And what we're doing there is we are manually engineering good layers or representations of our data. Right? This is also called feature engineering. And what deep learning does is it completely automates that step. We don't need to do that. And I've just highlighted those points here. So we've spoken so far about layers and transforming data. What does this mean in the context of a neural network? So the core building block of neural networks is the layer. It's a data processing module, and it can be thought as a filter for the data. So it's a core building block. That's what a layer is. So layers, more specifically, extract representations out of the data that's fed into them. And deep learning is the process of chaining together simple layers that implement a form of progressive data distillation. So we're going from one representation to the other to finally get to our output. So you can think of a deep learning model as like a sieve for data processing. It's made of a succession of increasingly refined data filters, which we call the layers. The specification of what a layer does to the input data is stored in its weights. So the weights define exactly what transformation the layer is applying. And in technical terms, we say that the transformation implemented by the layer is parameterized by its weights. So in this case, when we're talking about learning, what we mean is we're trying to find a set of values for the weights of all the layers in the network so that the network will correctly map example inputs to their targets or outputs. So, like, what does this look like mathematically? So on the left here, we can see what happens at a single node or neuron within the layer. So for this simple example, we can imagine that our layer is comprised of a single node, and we are mapping via this layer some inputs to outputs. So in this case, a single node is transforming this representation of input data, which is my x1 to xn, to an output y. So y is just another representation of our data. So how is this done? So we see that at the node, we have, or the nodes of the input data, they're all connected to this sort of node, this other node, and they all have a weight. And they're defined here as W1, W2, all the way to Wn. And what we can do is we can multiply our inputs, x1, by its weight, W1, and do this for all our inputs and weights, and then add them together. That's all it is. Then we apply some sort of bias term, and we can view this as like an intercept from a linear equation. We're just shifting our values around. And then what happens is this output is then put through what's called an activation function, which is just another mathematical function. And we will go into this a bit deeper later on. And then we get our output y. So that's all that happens in neural network. For this example, we've used a single node. What happens if we say we want to add more nodes? Like, what does that look like? So that's what this image on the right is. So here, my input data is just x1, x2, x3. These input nodes are connected to two other nodes in what we would call a hidden layer, so between the input layer and the output layer. And they all have a weight assigned to each connection. Now we can imagine that, for example, y1 and y2 would be connected to an output node, z1, which then transforms our data into our output, like we've seen on the left, y. In this example on the right, we haven't, or I haven't included any mention of the activation function or a bias. That's always applied. Once we've multiplied our inputs by our weights, summed them up, we still need to apply a bias and then put it through an activation function to get our output from y1 and y2. So on the left, I have just one transformation of the data, and then we get to our output. So that would be an example of shallow learning. On the right, you can imagine I've added this hidden layer Y1 and Y2, and then if that was extended further, we'd get to Z1, for example, which would be our output to give our output layer. So by adding these hidden layers is how we allow for deep learning. We're chaining these filters, these transformations of the data to find new representations. And back to this example on the right, I want to show that by adding this hidden layer, we could quite easily find the output values via matrix multiplication. So we have our weights in the blue matrix. We multiply them by our inputs. We would add a bias term, and then we would put that through an activation function to get our Y1 and Y2. So I hope that you come away from this slide with some intuition of what a layer does. A layer is just represented by a set of nodes, which are parameterized by a set of weights. We transform some input data into a new representation. So in the example on the right, we go from X1, X2, X3, that's our representation of our data, to Y1, Y2. And this is done using these weights, biases, and activation functions. We can then chain these layers together to make successive data transformations, and that's our deep learning. So to summarize, neural networks consist of chains of tensor operations, so that's the mathematical operations, and all that they are is geometric transformations of the input data. Now, I've gone over this very briefly, but the mathematical background of neural networks is taught really well in a Coursera course, which we have listed at the end in some additional resources, and I would recommend anyone who's interested in this to take those Coursera courses. Now, I find this next example a nice visual cue for what neural networks are trying to achieve. So we could visualize or interpret a neural network as a very complex geometric transformation in very high dimensional space via a long series of simple steps. So imagine, as you can see on the image on the right here, that I have two sheets of colored paper, one red, one blue, and they're both crumpled together into this paper ball, and that's my input data. And each sheet is a class of data in a classification problem. Now, how would I unravel that crumpled mess to get a nice two clean sheets that are clearly separable, and I can do my classification? So what the neural network is trying to do is figure out a series of simple steps, so transformations via layers, that ultimately uncrumple the two sheets of paper and allow the paper, or in this case, classes of data, to be cleanly separable. Again, in more technical terms, the neural network is finding neat representations for complex, highly folded data manifolds. Okay, so we have spoken briefly about activation functions, but why do we need them? So on the right, you can see some examples of common activation functions. And for example, we will see more of the relu and the sigmoid function later. If a layer could only learn linear transformations, that's what we've seen before with our matrix multiplication with our bias, if it could only learn linear transformations of the input data, the hypothesis space of that layer would just be the set of all possible linear transformations of the input data into some x-dimensional space where x is just the number of neurons or nodes you've chosen for that layer. That sort of hypothesis space is too restricted and would not benefit at all from multiple layers of representations, so chaining together these layers, so the deep stack of layers, because chaining together a bunch of linear operations just results in another linear operation. So adding more layers to your network would not extend your hypothesis space at all. So adding more linear operations still ultimately yields a linear operation. So how do we change this? In order to get access to a much richer hypothesis space that would benefit from these deep representations, so lots of layers, we need some sort of non-linearity, and that's what these activation functions are. They introduce some non-linearity to our hypothesis space. I hope that gives some sort of intuition as to why we need an activation function in our network. So now on to the sort of learning part of a neural network. So how do neural networks learn? So how do we update our weights and biases so that the resulting output from the neural network is correct? What we do is we use a loss function. So to control the output and adjust the weights of the layer, you need to be able to measure how far this output is from the expected. And that is the job of the loss function or objective function. We would then use this score from the loss function as a feedback signal to adjust the weights in a direction that will lower the loss score. So the choice of a loss function is usually based on what you're trying to achieve. For example, if I'm trying to do regression, I might choose the mean absolute error loss, or if I'm doing some sort of binary classification, then I might choose the binary cross entropy loss. And we won't go into too much theory as to what loss functions are suitable for what scenarios. That can be found quite easily online or in any sort of reading. So now we get on to how would we adjust the weights. So we've measured the loss score. We know how far away we are from what we were trying to achieve, the outputs that we want. How do we adjust the weights in the direction that minimizes that loss function, a loss score from the loss function? So this adjustment is the job of the optimizer. And common optimizers that you might see around are gradient descent or stochastic gradient descent or the Adam optimizer. And all the optimizer does is it's used to minimize that cost function, to adjust those weights. And there are plenty of options for this again, and it's not something that we'll go into today. But again, the Coursera course that's mentioned at the end of this covers this topic really well. And the optimizer implements what is called the backpropagation algorithm. So that's the algorithm to adjust the weights. So initially, the weights of the network are randomly assigned usually, which would naturally or most likely give a high loss score. But with every iteration, or in neural network terms, an epoch, the input data is fed to the network, the output is given, the loss function is calculated, and then the optimizer adjusts the weights in the direction of a lower loss score. And this is what we call the training loop. And this is repeated in order to minimize the loss function. So we're going to summarize here in the anatomy of a neural network what we've discussed so far. So we've covered the constituent parts of a neural network. We've covered the role of a layer, the activation function. We've covered the optimizer and the loss function. So how does it look in full programmatically? So we can see in this diagram on the right, we have some input X and some randomly initialized weights. These are passed, this input is passed to the layer. We do some sort of data transformation, that output is passed to another layer, and then we get our prediction Y. Then we'll compare our predictions to the true targets with a loss function to get a loss score. This loss score is passed to the optimizer, and the optimizer implements backpropagation to update the weights, which are then used in the next iteration or epoch of the training loop to get a new loss score. And we keep doing this until we minimize the loss function, until we've converged. So training a neural network revolves around the following objects: combining some layers into a network model, We have our input data and the corresponding targets. We have a loss function, which defines the feedback signal used for learning. And then we have an optimiser, which determines how the learning proceeds. So the topology of a network, so how many layers have I got? How many neurons within each layer have I got? This defines our hypothesis space. So by choosing some network topology, you constrain the space of possibilities to a specific series of tensor operations, some linear operations, and then our activation functions, which map our input to our output data. So picking the right network architecture is more of an art than a science. And that's something that you will develop with experience. There are some loose rules to follow, which we won't go over, but again, with the reading that we give suggest at the end of the presentation, that will cover this very well. So once the network is defined, you still have to choose two more things. You have to choose your loss/objective function, and then you have to choose your optimizer, and then you're ready to go. So what does that look like in practice? What does that look like in practice? Well, now we are going to classify some movie reviews by building our own simple neural network. So I'm just going to come out of our presentation, and I'm going to pull across this. That's the wrong one. That's a spoiler for later. So what are we doing? We are classifying movie reviews. It's a binary classification example with a simple neural network. So we're learning to classify movie reviews as positive or negative. So that's our binary classification based on the text content of the reviews. We're going to use the IMDb dataset. So this is a widely available dataset of 50,000 highly polarized reviews. 25,000 used for training and 25,000 used for testing. And each test set consists of 50% negative and 50% positive reviews. So we have a completely balanced data set. Nice example is taken from this book that I've been mentioning, Deep Learning with Python by Francois Chalot, and it is a fantastic book to get into the deep learning. So to begin with, I will import my libraries and what I need to do this. So we are going to be using some standard Python libraries, and then we're going to be using Keras, which is a TensorFlow API. And that's how we're going to build our neural network. So I'm going to load the dataset and split it into test and train. So I've got my train data, my train labels, my test data, my test labels, and this numWords equals 10,000 character. This argument here just means that we are only taking the top 10,000 most frequent words occur, so that to keep our data a manageable size. So rare words are discarded. So we can see that the types of our data is a NumPy array, and we can see the shape of this data. So it's 25,000 in each of the training and testing. So what does an individual training instance look like? So it's just a one-dimensional vector of integers like this, pretty boring. And what this does, so in our first instance here, I have 218 integers. And what these integers are is encodings for words. So the label here is a 1 for this instance, which means we are looking at a positive review. We can quickly check the max number of words in our training data, and we can see it's the 9999, which is why we've given the top 10,000 most frequent words. And then what we're going to do here is just make a function to convert the sort of integer-based format into actual text so we can read. So here I've printed the output from my function, decode review, the third instance, and we can see here that they were not happy with this film at all. So this has to be one of the worst films of the 1990s. So it does intrigue me as to what film this might be, but that's not what we're here for. So the next thing we've got to do is we've then got to prepare our data. So we can't feed a list of integers into a neural network. We have to turn this into a list of tensors. And to do this, we will one-hot encode the lists and turn them into a vector of zeros and ones. So for example, if I just had a review that was just 3 and 5, this might be really good, 2 words. I want to turn that into a 10,000 dimensional vector where I'd have zeros for every instance except for 3 and 5, which would be a ones. And I've done this by hand for clarity. So I've made a function here, vectorize sequences, passed it a sequence of words, and turned it into a 10,000 dimensional vector with zeros and ones. So here, I'm just vectorizing all my training data and my test data, and then I'm just changing its type. Yeah. So now our data is ready to be fed into the neural network. So we now get to the step of building our network. So the input data is vectors and the output data are scalars. So this is the easiest setup you can encounter, and the reason why I've chosen this example. A type of network that performs well in such a problem is a simple stack of fully connected, so they're called dense layers, where all my nodes or neurons in my layer are connected to all the nodes or neurons in the next layer with ReLU activations. And for example, the code to build in Keras, a layer like that would be this, dense 16. So dense is my class, the dense class. The arguments are here given 16 and my activation is ReLU. So 16 here denotes the number of hidden units or neurons in my layer. So a hidden unit is basically a dimension in the representation space of the layer. For a dense layer with ReLU activation, my output is just this ReLU activation of the dot product of my weights and my input plus my bias. So having 16 hidden units means that my weight matrix will have a shape of my input dimension and then 16, and the dot product with the weight matrix will project the data onto 16-dimensional space. Then you'll add your bias vector and apply the ReLU operation. So another way to describe this is to view the dimensionality of your representation space, which is given by your hidden unit or neuron value, as how much freedom you're allowing the network to have when learning internal representations. So more hidden units or neurons, we get higher dimensional space, which allows the network to learn more complex representations. But we have to be very aware of overfitting, and it's also more computationally expensive. So the 2 key architectural decisions to be made about such a stack of dense layers is how many layers to use and how many hidden units to choose per layer. So there are formal principles for this to guide you, which we won't go over today, but we're just going to start with a very simple architecture of 2 intermediate layers, so hidden layers with 16 units each, a ReLU activation, and then the 3rd layer will output the scale prediction. So that's a sigmoid activation, which gives us an output probability. So what does the ReLU function look like quickly? It's this for a given value of X. If I am below 0, if I'm negative, then the output is zeroed out. And if I'm above 0, it outputs some value. This is our non-linearity that we're introducing to the network. A sigmoid function is this. Given a value of x, it's squishing that value into a 0 to 1. Output, so a probability. So in Keras, we would define this model architecture here. So we create an instance of the model, the sequential class in models. We add our first layer, dense layer, 16 heading units, radio activation, and we have to give it our input shape. Then we add another layer, a dense layer with 16 hidden units, again, activation value, and then we're adding our output layer, which uses we have one unit, and it uses the sigmoid activation to give us our output. So like we've spoken about before, now we need to choose a loss function and optimizer. So for binary classification with a probability output, it's best paired with the binary cross entropy loss function. We'll be using the RMS prop gradient descent for the optimizer, and we will monitor the accuracy metric during the training as we have a balanced data set. So what we do here is we compile our model that we've just built with its optimizer, the loss, and the metric do you want to follow. And now we're going to validate our approach. So here I've set aside 10,000 samples from the training set for validation. So I make a partial X train and X val from my full X train, and I make a partial Y val, a partial Y train and Y val from my Y train, full Y train. We then fit our model to the partial X train, partial Y train. We want it to run for 20 epochs. This is how many times the training loop is executed. We've just given it a batch size. That's how many samples are fed at a time. And then our validation data that it's going to compare it against is our X val and Y val. And here is the output of what that looks like. And you can see the loss function is steadily decreasing as we go along. Our accuracy for the training set is going up, and then some stuff is happening with the validation accuracy, and we'll look at that now. So we can get from, we've created our history here. We can get from our history object, we can see that it's a dictionary, and it has the keys of our loss, accuracy, validation accuracy. So this is accuracy on our training set. And we're just going to plot those to see how this network is done. So this is the loss function here. At the bottom, we have epochs, and then we've got our loss function. So we can see for the dots, our training data, the loss function steadily is minimized for the training data. But what we see for the loss function on the validation is that it starts to minimize. It kind of bottoms out around 5, and then it increases again. And this is very indicative of overfitting. So what this is saying is my network is learning the patterns of my training data very well, but it's not generalizing very well to my validation data, my validation set. And that's not a good thing. We can see this in the accuracy. We can see the accuracy steadily increasing for our training data in our dots. And we can see it steadily increasing at about 5 and then starting to decrease. So we've built a simple neural network. It is overfitting, and there are ways to tackle overfitting, but we don't have time to go into that today. But hopefully I've just shown how simple it is to build a simple neural network in Keras. We can quickly have a look at some predictions. So we can use the model to make a prediction on our X test. We can just quickly round our predictions because they're some value between 0 and 1. And we want to have a look at some confusion matrix. We have a function to plot the confusion matrix. And here it is. So what we've got here is in our test set, we've got 10,961 true negatives, 10,274 true positives. We've got 2,226 false negatives because we've predicted negative and it's positive. And then we have 1,539 false positives because we've predicted positive and it is negative. So that concludes the portion on introduction to simple neural networks. I'm going to now hand over to my colleague Annelies to go over some more interesting network architectures. So yeah, I'll do that now.
Let me now introduce types of neural networks that can deal with memory as opposed to the networks we've seen before. These are typically recurrent neural networks. In ordinary neural networks, inputs are independent of each other, but in a recurrent neural networks, the inputs are actually related to each other via a recurrent connection on the hidden state, so that outputs from previous layers can also be used as inputs, leading to something like, well, what one could call memory. Parameters are shared across the different time steps. So here we can see this is actually a loop function over the state. And here we can see the parameters, U, V, and W. They are all shared across the states. So we have inputs here, X at t minus 1, X at time t, X at t time t plus 1. They indicate, for instance, a sentence, a sequence like, today the weather is fine, what is it? And then question mark. So each of those words could be a input. Some applications of R and Ns include sentiment classifications, but also sentence completion, such as in online tools, machine translation, but such networks can also be used for speech recognition and music composition. Standard recurrent neural networks are not good at remembering longer sequences though, such as paragraphs of text. There are types of networks which are better able to deal with long-term memory and with forgetting some of the information. These are LSTMs, and I get on to introducing these briefly now. A long short-term memory network is a type of recurrent neural network that enables the network to have long and short-term memory. The repeating module of a LSTM contains 4 interacting layers that we can see here. Well, these are the activation functions, and uses a cell state to keep track of the memory and gates to control the information flow of each cell. So we can see that here, and cell state indicated here. The main functions of the gates are a forget gate, which controls which part of the previous hidden layers information should be kept or forgotten. Then we also have an input gate, which decides which information to add from the actual input data. And also quite important to all of this, of course, is an output gate that checks what should be passed on as an output. LSTM layers can be stacked. One can have several LSTM layers on top of each other to build deeper LSTM networks. Often dropout layers are added for this as well, because dropout layers, they sort of probabilistically exclude certain nodes from being activated, and this can help with reducing overfitting. Now, typical applications of LSTMs are time series predictions, but also anomaly detection, such as in fraud detection, and also speech recognition, and in any areas really where RNNs, standard RNNs, have not been quite as successful due to the length of the input data, like paragraphs of text, etc. So these are networks that can deal with memory. Now I'm going to introduce another type of networks which have been very successful with basically image processing, computer vision, etc. And these are what are called convolutional neural networks. Convolutional neural networks are a specific type of neural networks that are very useful for computer vision and image recognition. A fundamental difference between a densely connected layer and a convolutional layer is this. Dense layers learn global patterns in their input feature space, whereas convolutional layers learn global patterns. CNNs also keep track of the geometry. For instance, in the case of images, they learn patterns found in small two-dimensional windows. This is a key characteristics which gives convolutional networks two interesting properties. Patterns that they can learn are translation invariant. After learning a certain pattern in the lower right-hand corner of the image, for instance, down here, a ConvNet can recognize it anywhere. And this makes ConvNet data efficient when processing images. They need fewer training samples to learn representations that have generalization power. They can learn spatial hierarchies of patterns. A first convolution layer will learn small local patterns, such as edges, and then a second convolution layer will learn larger patterns made of the features of the first layers, etc. This allows ConvNets to efficiently, basically, to learn increasingly complex and abstract visual concepts layer by layer. Now, convolutions operate on 3D tensors called feature maps with two spatial axes, height and width, as well as a depth axis, also called the channel axis. For a RGB image, which means red, green, blue image, the dimension of the depth is 3. But for a black and white image, this is 1, which indicates levels of gray in an image. The convolutional operation extracts patches from its input feature map and applies the same transformation to all of these patches, including a output feature map, producing an output feature map, which we can see here. This output feature map is still a 3D tensor. It has height, width, and its depth that can be arbitrary because the output depth is a parameter of the layer, and the different channels in that depth axis no longer stand for specific colors as in the RGB input. Rather, they stand for filters. Filters encode specific aspects of the input data. A filter, however, is a concatenation of multiple kernels, and each kernel assigned to a particular channel of the input. So in the example above, there is one channel, so the filter consists of one kernel. If the input data has multiple channels, a RGB image usually has 3 channels for red, blue, and a green channel. Then the filter will have 3 kernels and one of each kernel, one for each channel. Kernel values are learned by the CNN. Now let's go to the convolution operation in a bit more detail. What we can see on this slide is we have a example of a 2D convolution on 3D input data. Here we have red, green, and blue indicated as a basically for a RGB image, for instance. And now on the left, we can see that the first step, we have a first step where each kernel is applied to the 3 channels of the input layer separately to give new 3x3 matrices. Then you can see the second step on the right, where these 3 matrices are added together element-wise to get the output of this convolutional layer over here. Now, on the previous slide, a convolution was performed on a 3D volume. But typically, we still can call that operation a 2D convolution in deep learning. It's a 2D convolution on 3D volumetric data. The filter depth is the same as the input layer depth. The 3D filter moves only in 2 directions, height and width in the image. The output of such an operation is a 2D image with 1 channel only. This is illustrated in the picture on the left. Here, the input data, which is blue, has the same number of channels as the filter, which is orange, and thus it creates a 2D output. There exist also 3D convolutions. They are generalizations of the 2D convolutions. Here in a 3D convolution, the filter depth is smaller than the input layer, what we can see here, this example. As a result, the 3D filter can move in all three directions, height, width, and the channel of the image. In each position, the element ways multiplication and addition provides a number. So for instance, here, starting in that corner. Since the filter slides through the 3D space, the output numbers are arranged in a 3D space as well. The output is then a 3D data. Similar to 2D convolutions, which encode spatial relationships of objects in a 2D domain, 3D convolutions can describe the spatial relationships of objects in a 3D space. Such a 3D relationship is important for some applications, such as in 3D segmentations or reconstructions or for biomedical imaging, for instance, in CT or MRI technologies, where objects such as blood vessels usually, basically they follow a path in a three-dimensional space as part of the body. There are some other operations that are really quite important in conjunction with the convolutional neural networks. One such operation is padding. Now we have, for instance, in this case, we have pixels on the edge of the image, and we want to be able to apply a filter centered over these pixels as well. If we don't do any padding, this is not really possible. So padding, as we can see here, will help with that. Basically, as shown in the image on the left, if we move our 3x3 dimensional filter over the input image with a stride of 1 simply means moving the filter 1 pixel in one direction. It could also be a stride of 2 or whatever, but here it was just chosen a stride of 1. We can see that we get a smaller output. We have gone from a 5x5 to a 3x3 basically pixel size. And we can't center the filter over the pixels on the border. Now, if one wants to get an output feature map with the same spatial dimensions as the input, the solution is basically to add padding. Padding simply consists of adding new rows and columns to the original image, here and here, all around, which will be in support of the filter or kernel. The filter or kernel can use these new pixels. Usually they are basically set to 0 with values 0 as a support to then be centered along the pixels just along the border. We can see in this example on the right where the original image has been added by a set of pixels, padded by a set of pixels, that we get the same size of the image after this operation. So the original image and the output image have the same size. Padding is useful for this. Now, we have to be careful when we build these neural networks because the number of basically pixels with having filters and channels can increase a lot. And there's also the danger of overfitting. Further operation, which is usually max pooling, there's also average pooling, but in general, pooling is an operation that helps with these kind of things. Pooling is performed in neural networks to reduce variance and computational complexity. In short, the reason to use downsampling is to reduce the number of feature map coefficients to process, as well as to induce spatial filter hierarchies by making successive convolution layers look at increasingly larger windows in terms of the fraction of the original input of basically of the image they cover. Like in the image we had initially, the first layer only covered a small amount, small parts of the features. And then if we can sort of concentrate these small features into larger, bigger features, important ones, pooling can help with that. Max pooling is not the only way that can achieve such downsampling. One can also use strides over the convolution layers, but there is also average pooling, where each input patch is transformed by taking the average value over each channel of the patch rather than the maximum. Here we can see this is an example of max pooling. It takes in each corner, it takes the max value, sorry, in each patch it takes the max value. Here it's 9, in this one it's 4. Here we can see of these 3 by 3 values, it's 3 is the max and here 7, so that we get a max pooling output of this, what we can see on the right here. Now, max pooling tends to work better than these other solutions like average pooling. The reason is that features tend to encode the spatial presence of some pattern or concept over the different tiles of the feature map. And it is more informative to look at the maximum presence of different features rather than sort of the average, which is indicated here by picking the average of the number. This may be more illustrative if one has actual images. Right, now I'm going to have to talk as a last step also about how is the actual convolutional neural net built. And we need output as well that we can make use of. So what we do need to add as a last step in order to be able to have output, we need to add a fully connected layer so that we can get a output layer. Convolution layers identify the various features of the image for analysis. Pooling reduces the complexity in this process, and then a fully connected layer utilizes the output from the convolution and pooling process, and, for example, predicts the class of the image based on the features extracted in previous stages. So this fully connected layer is exactly what we have seen in the first part of this presentation, except now the input features are simply what has been extracted via convolution and pooling. So now there are weights and biases that come with this fully connected layer, and that can also be learned. We tend to flatten the output of the convolution pooling to then pass to a fully connected layer. So basically arrange it in 1 by whatever, how many dimensions we need in a 1 by however many dimensions we need layer here. Now, imagine how big and complex this fully connected layer would be without pooling, and thus the overfitting that can occur. So pooling is really important, because if we have basically a sequence of convolutional layers and we don't do any pooling, the number of nodes here would be really, really high, and the danger of overfitting is also considerable. So pooling is really useful for that. Now let's see this in an example. My colleague is now going to introduce an example of image classification where dogs versus cats images are fed into a neural network and then classified. Let me hand over to my colleague Tim now.
Okay. Let's go through an example of using a CNN. I hope everyone can see my screen. So we are going to use a simple CNN to classify images of cats and dogs. It's a classic example. The data has been taken from Kaggle, and the data contains 25,000 images for training and 12,500 images for testing. Again, this example has been taken from the book Deep Learning with Python. I think you are now seeing a pattern of how useful I found this book, and hopefully how useful you can find the book. Again, we start by importing all the packages that we need, and then I have set some variables which just have the data directory of the training directory where my training data is, and then the test directory. And you can see by me listing the files in these directories that I've got 25,000 files or images for my training, and I've got 12,500. Now, that is far too many for me just to run a small example on a notebook on my laptop. So what I'm doing here is making a small directory, which I've called dogs versus cats small. And then I'm making a subset of the training and test, and I'm making a validation set. So I've made a training, a small training set with 1,000 instances. I've made a validation set with 500 instances, and I've made a test set with 500 instances of pictures. And that's 1,000 of, so for example, the training set is 1,000 of dog and 1,000 of cat. So it's 2,000 total for the training set, 1,000 total for the validation set, and 1,000 total for the test set. And this is what the directory structure looks like now. And the reason why I've done this directory structure will be clear in a couple of cells, but it's so we can use some functionality in Keras, and it likes this directory data set. So I've got my dogs versus cats small, got my test data, cat and dog, my training data, cat and dog, and my validation set, cat and dog. So let's plot some dogs. So we can see some dogs. You can see each picture is actually of a different size. Some even have cats in them. Some have a human hand. So pictures, you know, they can be, there's a lot of variance in these pictures. And again, we will plot some cats. And we can see, for example, we've got a blurry picture. They're of different size. There's a human in this picture. So in this one, we've got 2 cats. So again, lots of variance that our neural network will have to deal with. So as the images are different size, we want to set them to a standard size. So what I'm doing here is I'm taking an instance of the image data generator class. I'm making an instance for my training and my testing, and I'm rescaling all the pixel values from 255 down to between 0 and 1. Then I'm making a generator. So my training generator, I give it my dictionary, and it automatically sort of recognizes this dictionary structure here. So training or recognize, I've got cat and dog, because I've given it flow from directory. And I've now set target size for the pictures. Now they're going to be 150 pixels by 150 pixels. And I've given a batch size of 20, so we want to feed 20 images at a time. And my class mode is binary because we are dealing with binary classifications. And you can see here, it's found 2,000 images that belong to 2 different classes. So 1,000 from dog, 1,000 from cat. I make a validation generator from the validation set that I made. Again, I've given it 150 by 150 as my target size in pixels and a batch size of 20. And you can see that it has found 1,000 images belonging to 2 classes, 500 cat, 500 dog. So here we can see from a train generator, I can actually get a single look at the shape of a single data batch and a single labels batch. And you can see for the data batch, I've got 20 instances in my batch. My height and width is 150 by 150, which we just discussed. And then I've got 3 channels. So these are RGB images. So I've got red, green, blue. So as Annelies discussed, now I would have 3 kernels, one for red, one for green, one for blue. Those kernels would make my convolutional filter. So I've got 3 channels in my convolutional filter, and that filter will run over this data of size 150, 153 and extract some features from that. So that's what my convolutional operation is doing. So now I want to build a model. And again, we are going to take an instance of this sequential class. And now we're going to add a convolutional 2D operation. Here is I've given just a dimension 32. Again, we're not going to go into how to choose these numbers in this. This is just simple example. I've given a 3x3 filter. So that's the size of the kernels, 3x3, that are going over the input data. And then I've given my input shape, and I've got a ReLU activation. Then I've got a max pooling, and again, it's a 2x2 matrix max pooling. So essentially halving the size of the data there. And then I've got another convolutional operation, then I've got another max pooling operation, another convolutional operation, another max pooling operation, and you see the pattern. Then we get to a bit where we flatten the output into that one-dimensional vector. So now my data is just a list essentially, and I densely connect that list to an output node. So each input will then have its own weight and its own bias, and then we have a ReLU activation for that, and then we add an output layer. So sorry, my dense layer has 512 hidden nodes. So that means 512 biases and weights associated with that. And then I've got an output layer, which is just one node, which is densely connected to these 512 nodes here. And I have a sigmoid activation because I want to output a probability between 0 and 1, or cat and dog. So here I can get my model summary. And the reason why I've outputted this model summary is to show this here. So the trainable parameters in this network is 3,453,121. So a lot of parameters. And that's even with the fact that we've got 4 max pooling layers. So halving the data each time. So with these convolutional operations, because you've got 3x3 filter, and all these different dimensions to deal with, you end up getting a serious amount of trainable parameters, and that's why we need this max pooling operation to even make this manageable. So I then compile my model like we've seen before. They're exactly the same. We've given a binary cross entropy loss function. We've given the RMS prop optimizer, and then we're monitoring the accuracy again, because again, we've got a balanced data set. I then fit this model to my train generator. I give some steps per epoch and an epoch value to how long I want it to run for. It's only my laptop, so I'm not trying to max this out here. I'm just trying to show how we would build a CNN. And then I've got my validation generator, which I want the model to validate on. And again, we've got the information per epoch here, my loss and accuracy on my training data, and my validation loss and my validation accuracy. So what does that look like? So in terms of the accuracy, we get a very similar scenario to what we saw with the simple neural network example. We see that for our training accuracy, we steadily increase. It's not entirely converged by 30 epochs. It could go for longer, but it's a different trajectory to what we see on the validation accuracy. That levels off and converges much sooner, maybe around epoch 10. So again, that's saying that the CNN is learning the patterns in the training data very well, but then not generalizing well to the validation data. And that's a balance that you obviously need to strike. So we're overfitting again. And this is what you tend to do when building a neural network, which is you tend to build a bigger network, you overfit that model, and then you apply some methods to reduce the overfitting and get a better result. So in terms of the loss, we see it steadily going down for our training data and not steadily going down for validation data. It's similar to what we've seen before. We haven't really converged by 30 epochs, but this is overfitting. So what does that look like in terms of just the predictions and results? So I'm using the same code as I did earlier, a function to plot the confusion matrix, and then have a look at the confusion matrix. So for our 1,000 test instances, I have 392 correctly predicted cat images, 315 correctly predicted dog images. I have 185 dog images that have been incorrectly predicted as cat, and I have 108 cat images that have been incorrectly predicted as a dog. So just because we've seen 2 examples of overfitting, I wanted to just briefly show that there are very simple ways to tackle that, and it's not that hard to code up. I can't go into the details of how these things work, but again, I can't recommend the book Deep Learning with Python any more than I already have. So there are many ways to deal with overfitting, but I wanted to show you with only some small tweaks we can tackle overfitting and improve our performance of our model. 2 common ways to tackle overfitting in CNNs is to use data augmentation. So take my training images, do some operation to that to generate new training instances, and something called dropout, which is essentially what it says in the tin. We're dropping stuff, dropping information from the network. So again, I make my training data generator, but this time I'm adding in some data augmentation operations to generate some more instances. I don't have to do that for my test data set, and I also don't have to do that for my validation generator. That there should not be there. It's fine. So then we create the same model that we've seen before, but now we're going to pass it the training data set with data augmented images as well. And we have also, with just 1 line of code, added in this dropout layer here. And we can see, so again, I get my summary, we've still got a lot of parameters. So this is also something that we could tackle, reducing number of layers, dimensions within those layers, and so on and so forth. But we've still got the same number of parameters. Again, I compile the model with the same loss, optimizer, and metrics that we've seen, and then I fit it to my new data, and I get this. So now you can see that the training and the validation accuracy are following a very similar path. We haven't converged yet. We would want to go for more than 30 epochs, but we've tackled the overfitting, and the same you see in the training and validation loss. We're seeing they're following the same trajectory. So we've with this simple example, we've just seen that with the addition of dropout and data augmentation, and if you're interested in this, go look it up, read what they're about and how they tackle overfitting. And we could also even improve this better by using other regularization techniques, and also tune the network parameters such as number of filters per convolution layer, number of layers in the network, and so on and so forth. So I hope this simple example has shown you, it's quite easy to get started with this stuff, especially with Keras. It's a very nice API, and there are plenty of example tasks that you can follow online. We've gone over cats and dogs. There's the MNIST data set, so classifying images of handwritten digits from 0 to 9. Plenty of stuff. So if you're interested, there's lots of material out there. Okay, so we'll get rid of this. We will go back to our presentation. Okay, so I've mentioned some sources and extra reading throughout the presentation, and here are some of them down on the slide. So we've got the books, we've got Deep Learning with Python, by Francois Chollet. We've got Deep Learning by Ian Goodfellow. Both excellent books. There are some fantastic Coursera courses. There's the Deep Learning specialization. There's also the Mathematics for Machine Learning, so some basics around linear algebra, multivariate calculus, and building that up towards looking exactly what happens into a neural network, how does backpropagation work, gradient descent, so on and so forth. And then the documentation for specific deep learning packages such as TensorFlow, Keras, and PyTorch. They're very, very helpful when it comes to getting started with writing some code. So yeah, thank you for coming to this seminar or this introduction to deep learning today. We really appreciate it, and yeah, thanks for your time, and hopefully you've enjoyed Royal Mail's group data science introduction to neural networks.
Yes, thank you for joining and for following this presentation.